Let's look at an example problem where we deal with adding vectors, in this case force vectors, to determine the acceleration of an object, in this case a bone that has a mass of 2 kilograms. Let's draw a picture. I'll draw bone. Not the greatest artist, but you get the right idea. We know its mass is 2 kilograms, and it's going to have some acceleration due to some different forces. The first force is Rex pulling on it with 10 newtons to the east. So I'll draw a force vector to the right. We'll call that 10 newtons. Fido pulls south at 15 newtons. So I'll draw a force vector that's longer, that's 15 newtons down. And then we have Max pulling at an angle north of west with a force of 20 newtons. This would be the west direction. That would be north. So north of west would be a vector that would start facing west and go 30 degrees north of there. So I should get a vector something like that, which is 20 newtons. And my angle in here would be 30 degrees. That would be the angle that is north of west. So if I add these forces, the sum of the forces equals the mass times the acceleration. And I have the three forces, and I'm just adding them up as vectors to get the net force. But the problem is all these forces are vectors, and they're all in different directions. So when we add vectors, you got to take into account that direction component. And so the way we add vectors is we create an XY table. All right, let's call this F1. We'll call this one F2. And we'll call this one F3, just from an organizational standpoint. So if I add F1, F2, and F3, I would get a resultant, all right, which would be my total force, right? It would be the sum of the forces, all right? And it would have a component that's in the x, and in the y. So let's draw what we know. So F1 acts in the positive x direction. It's to the right. So I'm going to put positive 10, and it has 0 component vertically. F2 is completely in the y direction, and it's downward, negative 15. Now F3 has a piece that's to the left and a piece that's up. So I'm going to break out F3 here. This is 20 newtons, but it has a component that acts to the left. This is F3 in the x, and it has a component that acts vertically, F3 in the y. And with that angle 30 degrees, I can do a little bit of trig. F3 in the y is going to be 20 sine of 30 degrees. Sine of 30 is a half, so that equals 10. And that's upward, so that would be positive 10 over here in the y direction. F3 in the x is going to be the adjacent side of that triangle, so I get 20 cosine of 30 degrees. Pull out my calculator for that one. 20 cosine 30 gives me 17.32, and it points left, so I'm going to put negative 17.32, and that goes in my table in the x direction. So I have all three pieces, and now I can add them up. In the x direction, I get a component that's negative 7.32, and then the y is negative 5. So those are my components of my total force. I would call that Rx and Ry, my resultant components. And so this bone is being pulled partially to the left and partially down. Now, let's use that and draw our components of our resultant. So I'm going to have an arrow to the left that has a length of 7.32, and adding vectors tail to tip, I'll put the 5 here, and it's down. And again, when we're doing the trig, we're only looking at the magnitudes. I don't need the negatives anymore. I have them accounted for in the direction of the arrows. And my resultant, R, would go from the start to the finish and would be at an angle theta. And we can calculate R using Pythagorean theorem. R would be the square root of 7.32 squared plus 5 squared. 7.32 squared. And then take the square root of that value. So R is 8.86. And that's in newtons. And we can get the angle theta would be the inverse tangent of the opposite leg, 5 over 7.32. Second tangent, 5. And that's 34.33. So my net force is going to be 8.86 newtons. That's the sum of my forces. And that has to equal the mass times the acceleration. So 8.86 equals 2 times A. And so my acceleration is going to be half of that, 4.43 meters per second squared. And we have a direction component. This is at an angle of 34.33 degrees. In this case, I would face west and go south of west. So I'm going to say it's south of west. So we had to take one more step once we had the force in order to find that acceleration. But if we know the net force, which is what that resultant would be, I can just divide it by the mass. So a good example, a nice vector problem adding forces, again looking at some direction components. Hope this helps.